So, the next speaker is an old colleague and friend. We were in the end of the 80s very interested in making the first attempt to make antibody libraries. And Gregory was the first to publish that in 1989, and a few years later he also, as the first group from MRC in the world actually, came up with a phage display of antibody libraries which totally revolutionized pharma industry. In that time also, we were just counting the number of Nature papers that sort of streamlined out of Greg's laboratory. It's totally impressive. I think he has a world record. He is also a very skilled entrepreneur. He is actually the founder of Cambridge Antibody Technology, where, for example, the Humira came out of. Today, Greg is the supreme leader of Trinity College, the master of Trinity College in Cambridge, and where he started many years ago, obviously. So it's really an honor, as I said, to introduce him. Another thing that's on a personal level impressed me always is that he starts his morning by swimming in his moat. Very few of us, Professor Timberland or anywhere else, can actually start exercise in his own moat. But apart from that, I guess the sort of the basis for the Nobel Prize wasn't that, but it was rather all the scientific in it. So it's great. Take the floor, please.
Well, it's a pleasure to be here, and thank you very much, Carl, for all that rubbish. The whole pharmaceutical sector at the top is already dominated by antibody drugs. And as Carl has alluded to, in the late 90s, we realized that in our attempts to actually isolate mouse fibromas, we realized that there were that it was possible to do this on a mass scale, but now take 1,000 B cells, and let's just do that. So we could then get 1 million combinations, of which only 1,000 would be original. So 999,000 would be new. Now that tells us we can break out of this whole issue of tolerance, because we can find antibodies, combinations, halide, that were never in there to start off with. And therefore, if we could search those, we might find ones in there that could react with the human, proteins. Now the question is, how do we screen millions of these antibodies, millions of these clones? And we thought of a number of different approaches. Actually, very fortunately, at the beginning, we had come across George Smith's paper, and we thought, this would be easier if it worked. Furthermore, these antibodies here, that I marked at the bottom here, have already found their way onto the market. So these are approved drugs coming from the phage display. We could then apply phage selection, all the methods of phage selection to this, and we found that we were able, because of this constrained nature of the peptide, we found we could generate high affinities. So that's triple negative breast cancer. This is sarcoma. Tumor volume here, again, if we look at the 10 mg per kg, we're getting, or in fact, I think we've got this is 10 mg per kg bi-weekly, or actually single weekly. All of that essentially brings the baseline down to 0 tumor volume. But if we start taking with that 1,000 milliliter, when the tumor is 1,000 milliliter acute, if we actually start giving it the bicycle, you may be able to see here that this is greatly diminished, and as we continue this treatment, essentially it's tumor-free. So you can take out, in this case, a large massive tumor by this strategy. The whole issue of immuno-oncology, the excitement was to realize that essentially T cells, they can be T cells in a tumor that's directed against a tumor target, but they've been turned off. So they're not doing anything quiescent. And there's a kind of couple of pedals on the tumor cell. There's a gas pedal, you can actually turn them on, another one you can turn them off. So we're hopeful that this evolution technology, which we use for antibodies, can in a similar way be extended to this type of new, but I hope will be a new pharmacological entity. Thank you.